In this course, you'll see how Cosmos SDK, CometBFT, and the ABCI++ interface fit together to form a production blockchain stack, and how to shape block proposals, votes, and modules so they behave predictably under real-world load and failure conditions. When you design a blockchain, you're really designing how the network survives failure and upgrades over time. A traditional monolithic system has a single point of failure. One microscopic bug, one misconfigured node, or one privileged admin can compromise the whole thing. Cosmos takes the opposite approach. Consensus is decentralized, cryptographically enforced, and modular. The chain's structure is reinforced by many independent validators, all verifying the same rules. As we go deeper into CometBFT and ABCI++, keep this mental model in mind. You're engineering structural integrity, not just writing business logic. Strong Cosmos SDK apps start by separating concerns. Think of your module as three main layers. First, types. This is your public contract. Messages, params, events, errors, and any structs other modules, clients, or tests depend on. Keep it small and stable. Second, the keeper. This is internal business logic and state access. It depends on types, but not on CLI or simulation. Third, wiring and integration live in module. Go plus client, simulation, and Genesis helpers. This separation keeps imports acyclic, testing straightforward, and upgrades much safer. For Cosmos SDK modules, code structure is not cosmetic. It directly affects correctness and reviews. In the before version, you often see huge handlers that mix validation, state access, and events in a single function. Naming is fuzzy, responsibilities blur, and it becomes hard to reason about invariance or safely change behavior. The after version leans on Go idioms and domain-specific names and extracts clear helper functions for each concern. That smaller, well-named surface area makes it much easier to audit ABCI paths, spot bugs, and add new logic without breaking consensus. Dependency hygiene is what keeps a Cosmos SDK codebase from collapsing under its own weight. Your types package should be completely ignorant of keepers and other heavy dependencies. Treat it as your pure domain model. All wiring between modules belongs explicitly in your app or module. Go, using constructors like newkeeper for dependency injection. That discipline gives you acyclic imports, clean interfaces, and testable modules. Any shortcut, like importing other keepers inside types, may feel convenient early, but it tightly couples modules and makes refactors and ABCI++ changes painful later. Deterministic behavior in Cosmos SDK work starts with how you handle context, errors, and builds. Always thread a context. Context through your module APIs and ABCI logic. That lets you cancel work cleanly on timeouts, shutdown, or height changes. Prefer deterministic typed errors over panics. Panics should mean this process is unrecoverable, not a user sent bad input. And lock your toolchain. Pin. Go and all module versions in go.mod. So every node compiles identical binaries, which is essential for consensus. Think of your testing strategy as a pyramid for your chain's structural integrity. At the base, unit tests hammer on keeper methods and pure functions. Here you verify invariants, edge cases, and error handling with fast, deterministic checks. In the middle, integration tests exercise MSG and query servers. These ensure your module wiring, codecs, and state transitions behave correctly when a real request flows through the app. At the top, simulations run randomized, long-lived workloads against the whole application. They expose emergent bugs, bad interactions between modules, and performance issues you'd almost never hit with handcrafted cases. Keeper isolation testing treats your keeper like a pure component. Instead of spinning up a full chain, you wire it to an in-memory KV store and mock any external modules it depends on, like bank or staking. That lets you hit every edge case cheaply and deterministically. With that setup, you can aggressively assert on state transitions, emitted events, and boundary conditions without consensus noise hiding subtle logic bugs. Missed server tests are where you prove your module's interface is actually safe to use. Start by spinning up a realistic test harness with something like setup msgest server. T. Treat it as your public firewall. Every message must either pass or be rejected loudly. Verify that your handlers enforce auth decisions. Then layer on protobuf, validate basic, so malformed payloads never hit state. Finally, hammer edge cases. Pagination bounds, invalid IDs, and expected error codes. and assert that successful calls produce exactly the state transitions you designed. App module simulation is basically chaos engineering for your modules. Instead of writing one-off tests, you let the framework hammer your chain with random parameters, random genesis states, and random sequences of operations. Your job is to define invariants, properties that must never break, like total supply conservation or non-negative balances. If any invariant fails during simulation, you've found a serious bug long before mainnet. Treat your architectural docs as the single source of truth for the chain. Keep a top-level README that explains the big picture, modules, data flows, and how they relate to ABCI and ABCI++. A new engineer should be productive after reading only that file. Be ruthless about documenting state. Every KV store, key, and prefix needs a written contract and invariants. And maintain a catalog of all MESG types, queries, and events, so downstream services and dashboards never have to reverse engineer behavior from the code. Architectural Decision Records, or ADRs, are your project's design logbook. Each important decision gets its own small document, with an ID and a clear title. In it, you record the context, the choice you made, the main alternatives you rejected, and the consequences. Over time, this gives you a traceable history of why the chain looks the way it does, and lets future maintainers audit or safely revisit past decisions. Treat your Cosmos SDK documentation exactly like code, versioned, reviewed, and tested as part of every change. In practice, any PR that alters behavior or APIs must include matching doc updates or an explicit ADR. Wire this into CI. Fail builds when docs or ADRs are missing, and add checklist items to code review templates. Aim for small, frequent ADRs that describe a single decision. They're easier to review, easier to revert, and they keep your architecture history tightly aligned with the evolving codebase. For Cosmos SDK chains, treat code review as your first consensus layer. You want strict, repeatable checklists so reviewers don't improvise safety. Structure, naming, and test coverage are table stakes. Keep pull requests tiny. If a change can't be reverted with one click during an incident, it's too big. Every PR should show that state transitions are atomic and reversible, especially around ABCI++ hooks, and require two kinds of reviewers: a domain expert who understands business logic, and a consensus or security expert who thinks in failure modes. As you start building real Cosmos SDK chains, treat your codebase as an engineered system, not a pile of modules. Enforce predictable organization, a consistent layout for apps, modules, keepers, tests, and ADRs, so new features land in obvious places and velocity stays high as the code grows. Aim for layered defense testing. Unit tests protect invariants, integration tests protect flows, and simulation or fuzzing protects the unexpected edges. Finally, wire in rigorous security checkpoints, mandatory reviews, automated linters, static analysis, and invariants in CI. That discipline is what lets you safely ship advanced ABCI++ logic to production.